This is the lab lecture for the determination of molar mass by freezing point depression. I want to go in and talk about some background material here that you might not have got to in the lecture yet. Alright, so I want to start out here by talking about phase changes. If you take a solid and you heat it, heating a solid, the temperature will increase. Temperature will increase steadily, okay, until you get to the melting point. Well, once you get to the melting point, your temperature will level out and it will remain constant while the phase change is taking place until all of the substance is melted. In other words, until all of it exists as a liquid. So what's going on here? Let's say your substance melts at 6 degrees Celsius. It's frozen, and you pull it out, and the room temperature is 25 Celsius, so heat is flowing into it. But once the phase change starts, there's no further temperature increase. Why is that? Because the energy input is used to achieve the phase change rather than heat the sample. It takes energy to overcome the intermolecular forces of attraction in the solid and become a liquid. Okay, so the heat of fusion is the energy required to melt 1 mole of your compound. Now, once you get past the melting point, once all the substance is melted, then the temperature will start to go up again. And it will go steadily up again until you reach the boiling point. And then you're going to have a second plateau where the temperature remains constant because you're now having boiling taking place. All the liquid is being converted to a gas. So that is the heat of vaporization. The energy required to vaporize 1 mole of compound. That's almost always bigger than the heat of fusion, okay, because it takes more energy to go from liquid to gas than it does solid to liquid. But anyway, it's the heat of fusion, it's the melting process that we're going to be using here. So we have a graph like this. If you took the solid and you steadily heated it, and you recorded the temperature versus time, your graph would look something like this. It would start out as a solid. Your temperature would steadily go up, okay? Then you would reach a point where the temperature remains constant. That's the first phase change. That's their melting. That's where solid is being converted into a liquid. Once all the solid is melted, it exists all as a liquid, then the temperature starts to go up again. Here we have only liquid. Okay? Then temperature goes up. We reach the boiling point. Now we have another plateau. Now we have liquid being converted into gas. That's vaporization. Once it's all vaporized, it exists solely as a gas, and then the temperature can start to go up again. So there's a couple of things that I want to talk about here with solutions. What's a solution, and how do you measure the typically measure concentration of solution? Right, so a solution is one substance dissolved up in another. The solvent is usually, or not usually, the solvent is a substance that does the dissolving. That's present in the larger quantity. The solute is the substance that is dissolved. That's present in the smaller quantity. So, for example, when you dissolve sugar in water, the water is the solute, the water is the solvent, the sugar is the solute. One more time, water is the solvent, sugar is the solute. What are some ways of expressing concentration? In other words, how much solute do we have dissolved up in our solvent per unit volume? That's molarity. All right, so molarity is moles of solute per liter of solution. So to make a 1 molar solution, you would take a mass equivalent to 1 mole, and you would dilute it, add enough solvent to make a final volume of 1 liter. It's a subtle but important point that the exact volume of water, it doesn't have to be water, whatever solvent you're using, but the exact volume of water added is not known. You don't keep track of how much solvent you add. You're just adding enough solvent to make that liter of solution. So the ratio of solute mass to solvent mass is not known. The only thing that's known is the number of moles of solute per unit volume. This is so commonly used because it's typically very convenient and fast to measure a volume in a lab. So you measure a volume, you pour out so many milliliters or liters of a solution, you'll know how many moles of solid you have because you know the ratio of moles of solid to liter of solution. Molality is different. That's lowercase m. Molarity is uppercase M. Molality is lowercase m. That's the moles of solute per kilogram of solvent. So here you have to physically measure the amount of solvent that you're adding. So you know the ratio of solute mass to solvent mass, or stated another way, you would know the ratio of moles of solute to moles of solvent as well. It's a subtle but important difference between these two ways of measuring concentration. So colligative properties are properties that depend upon the number of particles in solution. When you dissolve up a solute in a solvent, you change the properties, the physical properties of the solvent. And one of these is freezing point depression. Okay, a solution with a dissolved solute has a lower freezing point than that of the pure solvent. Okay, that's one of your colligative properties. You lower the freezing point. So we can calculate freezing point from this equation. Delta T is equal to KFM. All right, now, so M is what we just talked about. Lowercase m, that's the molality of the solution, and Kf is the freezing point depression constant of the solvent. Just to throw out a couple of examples, for water, that's 1.86 degrees Celsius per molal. For cyclohexane, that's 20.4 degrees Celsius per molal. Now there's a couple of things that I want you to note here. Number one is these are very different numbers. Every solvent has a unique freezing point depression constant. Second thing I want you to note is to look at this unit, degrees Celsius per molal. In other words, how many degrees Celsius change in freezing point do we get per molal concentration? Okay, and then one more thing too is look at this. Delta T is what we're measuring. Delta usually means change, correct? So we're measuring the change in the freezing point. This is not the absolute freezing point. It's the amount by which the freezing point is changed. So if we wanted the absolute freezing point, we would have to go and subtract this from the freezing point of pure solvent. This only tells you how much the freezing point is changed. So here's what we're after. Some calculations. We can break this down into 3 steps. What we're after is the molar mass of a solute. We're going to dissolve up a solute in the solvent. We're going to measure the freezing point of the solvent. We want to know the molar mass of the solvent. To get the molar mass of the solute, rather. To get the molar mass of the solute, we're going to need to know the number of grams, and we're going to need to know the number of moles. grams per mole, or the unit on molar mass. So first thing we're going to do is by measuring the change in the freezing point. And the change is that of the solution versus that of the pure solvent. It is possible to calculate the molality of the solution, right? So we take our equation for freezing point depression. Delta T is equal to KFM, and let's rearrange it and solve it for the molality. If we know the change in freezing point and we know the freezing point depression constant, then we can calculate the molality of the solution. Okay? So then, from the molality of the solution, we can get the number of moles of solid. Because we can take the equation for molality and rearrange it to solve it for the number of moles of solid. So if molality is moles of solute per kilogram of solvent, let's rearrange this for moles of solid. Moles of solute is then molality times the kilograms of solvent. Okay, now, so if we know the molality and we know the number of kilograms of solvent, then we can calculate the moles of the solute. How many moles of solute did we put in there? Okay, so the mass of the solvent has to be known. We have to know the kilograms of solvent. Or in the way we're going to do it is to measure out a specific volume, because cyclohexane is a liquid at room temperature. We're going to measure out a specific volume and then use the density to calculate the mass. Okay? And then last, what are we after? We're after the molar mass of the solute. Molar mass is grams of solute over moles of solute, grams per mole. So basically, we'll know the grams of the solute because we're going to measure how much solute we put in there. And the moles of solute we're going to get from the freezing point depression data. So we'll know the mass of the solute, we'll know the moles of the solute, and we'll be able to calculate the molar mass of the solute from the freezing point depression data. So let's work an example problem here. And this is exactly like the calculation you would do in the lab. So let's suppose that 0.10 grams of an unknown solute are added to 10 mils of cyclohexane. The resulting solution freezes at 3.8 Celsius. What is the molar mass of the solute? Right, so there's three things we're going to have to know. We're going to have to know the normal freezing point of cyclohexane. That's 6.6 Celsius. Knowing the change in freezing point tells us nothing unless we know the normal freezing point. So the normal freezing point for cyclohexane is 6.6. The density of cyclohexane is 0.78 grams per milliliter. And the freezing point depression constant for cyclohexane is 20.4 degrees Celsius per molal. So the first thing that we have to do is calculate the freezing point depression, the change in the freezing point. So cyclohexane normally freezes at 6.6. Our solution froze at 3.8. So that's a change of 2.8 Celsius. That's how much we depressed the freezing point. Now again, we'll take the equation for freezing point depression and rearrange it to solve it for molality. Molality is the change in freezing point divided by the constant. So 2.8 degrees Celsius divided by 20.4 degrees Celsius per molal, that is 0.14 moles per kilogram, right? That's the unit on molality, moles of solute per kilogram of solvent. Then we need to figure out our mass of solvent. right? Well, you weren't given a mass of solvent, you were given a volume. So we're going to have to go from the volume and use the density to get the mass, right? So that's why you were given the density of cyclohexane. So 10 mils times 0.78 grams per mil. Now, pay attention to units though, because molality is moles of solute per kilogram of solvent. Right now, this converts it into grams. Milliliters times grams per milliliter. The milliliters will cancel, and that gives us grams. So we have to do one more conversion into kilograms times 1 gram over 1,000 grams tells us we had 0.0078 kilograms. Well, now we can say 0.14 moles per kilogram times the number of kilograms, right? We have kilograms on the bottom, kilograms on the top, so those will cancel. So 0.14 times 0.0078 is 0.0011 moles of solid. Well, now we're home free, right? Because we know how much solid we put in. We put in 0.10 grams, 0.10 grams, and 0.0010 moles. So molar mass is grams per mole. So 0.10 grams divided by 0.0011 moles is 91 grams per mole. Okay? So what are we going to do in the first week? So what are you going to do in the first week? The first week is just going to be pure cyclohexane. You're going to construct a heating curve for pure cyclohexane. So you'll construct the ice bath as described in the text. It's basically ice and salt. We have to use the salt to get the temperature down as low as we can. So you're going to use a graduated cylinder to measure 10 mils of cyclohexane and add it to the tube along with a wire stirrer assembly. You're going to clamp it and hold it until slushy, right? So we're freezing the cyclohexane. Cyclohexane freezes at 6.6 Celsius. The temperature of the water bath or the ice bath might get as low as -1 after you've added the salt, maybe even -2. Cyclohexane will definitely freeze, okay? So you're going to raise it out of the bath, out of the ice bath, and record the temperature every 30 seconds. You do not start recording data until you take it out of the ice bath. We're making a heating curve, not a cooling curve. All right, so you'll clamp it in the ice bath till it's frozen, pull it out of the ice bath, and then record the temperature every 30 seconds as it melts. You'll construct a graph of time versus temperature for pure cyclohexane, and you'll record the melting point of the pure cyclohexane from your data. So your apparatus will look something like this. You just basically have it's not too fancy. You have a beaker that will be packed with the ice salt mixture, test tube, which will have the 10 moles of cyclohexane, and the thermometer. And they didn't show it here, but you had there'll be a copper copper wire bent that you can use to keep the solution stirred to keep it mixed. So how are you going to know what your freezing point is? Where the temperature stays constant the longest, right? One more time, it starts out as a solid, and the temperature remains constant as it goes from a solid to a liquid. So that's what you're going to be looking for, where the temperature stayed constant the longest. It probably won't be as perfect as it is here. It probably won't be as perfect as it is here, but you'll be able to tell what the freezing point is. You'll want to pick the temperature where it stays constant the longest. And then the second week, you will do almost exactly the same thing, except we're going to add 0.2 to 0.3 grams of an unknown solid. This time, a precise volume of the cyclohexane must be used. So that 10 mils needs to be measured as accurately as possible, and you're also going to record your exact mass of the unknown. It says 0.2 to 0.3. Anywhere between 0.2 and 0.3 is fine, but you have to record the exact mass that you used out to as many decimal places as the balance will give you, which should be 3 places past the decimal. And that pretty much wraps this up.